I used the same amount of material to build a truss and a beam bridge and loaded them to failure. But before we get to the destructive testing, let us see how these bridges work in theory. If you're not interested in hearing about these engineering concepts, skip directly to the tests near the end of the video. But I do encourage you to stay. By the end of the video, you will have a better theoretical understanding of trusses than the bridge builders from the 1700s that were great at constructing these structures but didn't really know how they stood up. We have already talked on this channel how beams carry loads. They bend such that the top of the beam is getting compressed and the bottom of the beam is being stretched. The combined action of these forces plus the shear resistance is what transfers the load to the end supports. The further apart these forces are, the higher the bending capacity of the beam is. Hence, why the wide flange beams have most of their cross-sectional area offset to the top and bottom of the beam. The truss takes this concept to the next level. If you think about it, the truss is basically a beam where the top and bottom flanges are structural members of their own. The beauty of the truss is that all of its members are only subjected to axial loads, which makes the whole structure efficient and also incredibly stiff. This may not be obvious, so let's have a deeper look. But just to be clear, stiffness in engineering terms means the amount of load a structure can take per unit deformation. Or another way to think about it is what load causes the structure to deform by 1 millimeter or 1 inch or whatever unit you prefer. Intuitively, you know that it is much easier to deform a member by bending it rather than compressing it. So it follows that bending members, such as beams, exhibit low stiffness for longer spans. This is because the stiffness of a simple beam is scaled with the cube of the length of the span. This means that doubling the length makes the beam 8 times more flexible. If you have worked with long beams, you have probably noticed how wobbly they are compared to shorter beams of the same cross-section. Now, trusses do not have bending members, so this formula does not directly apply. Trusses are arranged in such a way that all of its members are loaded axially. The stiffness of axially loaded members scales linearly with the length. So, axially loaded assemblies are naturally more suitable for longer spanning structures, such as bridges. However, it takes a little bit of thinking to arrange such assemblies of elements in a way that all of the members are axially loaded, yet they span a longer distance. One way to achieve this is to construct an arch or a trestle bridge, as our ancestors did. Still, these bridges require frequent piers that are not always possible, especially not in deep waters. The truss is an alternative structure that doesn't require regular supports and yet uses the axial stiffness of its members. In fact, the high stiffness of the truss is why it is often used for railway bridges. Railways have very strict deflection requirements because an excessive deformation of the bridge and rail would lead to a derailment of the train. For that reason, even today, bridges that serve as a rail connection utilize some sort of a truss structure within them. Suspension bridges, due to their high flexibility, very rarely have railway traffic, unless the deck is stiffened with a truss-like structure. Let me know in the comments if you know of any purely suspension bridges open to railway traffic, or any cool bridges in general. Trusses do also have disadvantages. For example, buckling of the compression element, increased construction complexity, and so on. Depending on the length, the effects of these parameters determine the feasibility of a particular bridge type. Beam bridges, due to their low material utilization but ease of construction, are the preferred choice for spans of up to 100 meters. Beyond 100 meters and up to 300 meters, the truss becomes the optimal bridge choice. For even longer spans, the cable-stayed and suspension bridges become optimal. In many cases, a combination of these techniques is used. The truss is efficient because its members do not bend. But it feels like we still haven't explained why this is the case. Why do truss elements not bend? Our intuition suggests otherwise. When elements are loaded perpendicularly, they should be bending. In the case of the truss, the overall structure is bending, but its individual elements are not. They're only being compressed and stretched. There are 2 main reasons why this is the case. The first reason is because trusses are usually only loaded at the joints. This is not always obvious, but if you have a closer look at a truss assembly, you can see that the deck is usually not directly attached to the truss itself, but it's resting on floor beams that run in a perpendicular direction. The floor beams are then connected to the joints where the load is distributed into the truss and then transferred to the end supports. The second reason is less obvious and requires a slight understanding of statics. In engineering, the joints of a truss are modeled as pin connections, which means the members can freely rotate around the pin. But in reality, we never see these pins. In fact, we see heavy gusset plates scattered with dozens of bolts. Surely this cannot be a pin. Well, it's not an actual pin, but the connection does behave like a pin as long as a very important condition is satisfied. The requirement for the gusset connection to behave as a pin is that all of the connected members intersect at the same point. If they do, then there are no couple moments generated at the joint. In contrast, if one of the members was installed incorrectly and did not intersect at the same point, then for the joint to be in equilibrium, there has to be a bending moment present. This becomes obvious if we sum moments about the intersection point, which clearly leads to a non-equilibrium condition, which can only be balanced by bending of the offset member. Of course, in reality, the connected members are not perfectly intersecting, but as long as they satisfy a particular tolerance, then the pin assumption holds and the structure is incredibly efficient. Now, let's see a practical example of a Warren truss compared to a beam of the same cross-sectional area. I decided to go with a Warren truss, mostly because all members are of the same length, so it was supposed to be easier to cut and build. My craftsman skills are limited, so as you can notice, the truss is far from perfect. The beam was significantly easier to build since it was only about gluing the sticks together. Even though these are far from real bridges, they do, to some extent, reflect on the difference of man-hours required for each structure. For that reason, the beam bridge is sometimes preferred. From a material point of view, the beam is less efficient, but the extra material expenses are quickly recovered due to the simpler construction. The loading was performed with a bucket of wet sand hanging under the table. For brevity, only the final stage is shown here. The truss managed to carry 45 kilos or 99 pounds before failing. In reality, a better constructed truss would have performed much better. Also, the failure was not pure tension failure, but had a significant amount of bending and sideways twisting, which would not appear in a real structure as we discussed earlier. I know this experiment is far from perfect. I will try to get better in the future, so try not to be too harsh in the comments. The beam, on the other hand, performed fairly decent and reached 38 kilos or 84 pounds, which is probably close to its real capacity, since it did not suffer from significant construction deficiencies. In summary, besides the poor construction, the truss still managed to outperform the beam by more than 15%. Depending on the application, this 15% difference, or possibly more, might be the deciding parameter for going with a truss rather than a beam bridge. But truss structures do not appear only in bridges. You can find them in roofs, large venues, antennas, and many other places. This video is a good introduction, but if you want to take your understanding to the next level, you can check out the courses provided by today's sponsor, Brilliant. Brilliant is an interactive learning platform that helps you grasp complicated STEM topics through intuitive explanations and hands-on lessons. Brilliant has lessons on Newton's laws, statics, kinematics, even a specific lesson on truss and beam bridges that explain in a bit more detail the theory behind these structures. The best thing is that the interactive visuals and intuitive explanations are so natural and entertaining that it completely takes away the feeling of a boring lecture room while achieving deep conceptual understanding. Head to brilliant.org/The Engineering Hub to get started for free with Brilliant's interactive lessons. The first 200 viewers will also get 20% off on an annual membership. You can find the link down in the description. Thanks for watching. If you liked the video, consider giving us a thumbs up and also subscribing to our channel.